So this is my first A-level physics video, so please be kind. And I'm not going to promise to get every single part of the spec in here, but I'm going to give you a nice overview of stellar evolution and then the HR, the Hertzsprung-Russell diagram. There'll be quite a lot of just talking. It won't be all written down because there's a lot to talk about and I couldn't fit it all on the page. But a lot of this is recap from GCSE, especially stellar evolution. And I like this diagram here because this diagram shows us that stellar evolution is a cyclical process. It's not that a star is born, it dies, and that's the end of it. When a star dies, the remnants of the star become the new stars. And we've got two different types of process going on here. We've got stellar evolution for sun-like stars on this side, or sun-like stars are also called medium-sized stars. And then we've got stellar evolution here for massive stars. And the first thing to notice is that they both come from the same thing. They both come from here, and this is a stellar nebula. And a stellar nebula is just a cloud of gas and dust, often from old stars, or in earlier times, clouds of gas and dust that had been around since the Big Bang, or just after really. So they both start from the same point, and then you might notice that my sun-like star circle, or life cycle as it were, is bigger than my massive star circle, and that is because sun-like stars have a much longer life cycle than massive stars. Massive stars have a lot more fuel because they're bigger, but because of that, because they're bigger, they burn through their fuel much more quickly, so they literally do live fast and die young. And the life cycle of a massive star can be about the 10th of the life cycle of a sun-like medium star. I often compare it to if you've got cars. So I have a little Fiat Panda, and one tank of petrol will do me quite a lot of journeys. It's a small tank of petrol, but the car doesn't use much petrol, therefore I can go a long way on it. If you've got a big sports car, the tank of petrol, or the tank will be much bigger, but you won't get as far because the car burns through more of that petrol per kilometre. So massive stars have shorter life cycles because they literally live fast and therefore die young. So I'm going to start with the sun-like star. So a stellar nebula is a cloud of gas and dust, and what you'll find is within that stellar nebula there'll be one bit of gas and dust that's slightly more dense than the gas and dust around it, so like maybe this little section here. If it's more dense, that means it has more gravity because it has more mass, and therefore the cloud begins to collapse in on itself. It collapses due to gravitational forces, and as the cloud collapses, this dense section of gas and dust gathers more gas and dust and therefore gets denser and denser and denser. As it gets denser, it also gets hotter, because as the gas falls into the into the denser part, it gains kinetic energy and it loses GPE. And as it gains kinetic energy, particles with more kinetic energy are by definition hotter. Gases with more kinetic energy are hotter than those without. And it also, as it's getting denser, gets higher pressure. So we're getting hotter and hotter, the pressure's getting higher and higher, and eventually you get to a point here where I've tried to show it a little bit, where you get a protostar. And a protostar is when you've got this kind of cloud of gas and dust, nice and dense, nice and collapsed, and it's ready to become a main sequence star. So this is a protostar, and the same thing happens here as well for both high mass and low mass. It's just for a high mass there's more in the protostar, although my drawing doesn't really show that. Then when it's hot enough for fusion to start, for hydrogen to turn into helium, that is when it becomes a main sequence star. So the main sequence star is when fusion of hydrogen to helium begins. So a protostar isn't fusing, and when it gets hot enough and dense enough and high enough pressure enough, then fusion can begin, and it's now a main sequence star. And a main sequence star is where the star will spend the vast majority of its lifetime, about 90% of its life. For sun-like stars, that main sequence is about 10 billion years, and our sun is about halfway through that. Our sun is actually a slightly smaller than average medium star, or a slightly smaller than average star, which is why we call them all sun-like, because it's basically average. So the main sequence, we've got hydrogen fusing into helium, and it's nice and stable. And while it's stable, there's two forces that kind of compete throughout all of stellar evolution, and that is gravity versus thermal pressure. You often just hear it called pressure. Now, gravity is due to the mass of the star and is always pulling the star inwards, whereas thermal pressure is pushing the star outwards. And the hotter the star is, the more thermal pressure there'll be. And it's a tug of war between these two forces. When gravity is bigger than thermal pressure, the star will contract. And when thermal pressure is bigger than gravity, the star will expand. So, in the main sequence, we find that gravity and pressure are balanced, and that's where the star is stable and stays the same size. And like I say, it's approximately 10 billion years. Eventually, what's going to happen over here, so this is the whole of the main sequence, is that the hydrogen is going to run out, and the star will run out of fuel. Now, fusion can happen for other elements. Helium can fuse to create heavier elements, but for that fusion to take place, the temperature needs to be higher. Fusion's pretty tricky because you've got two hydrogen nuclei, basically two protons trying to join together. They're both positive, they don't want to join together. So they have to have really high temperature, high pressure conditions to overcome the electrostatic force of repulsion between them and then fuse together to make helium. So helium, which has got two protons in its nucleus, to have two heliums fused together, you need even higher temperature conditions. Now, that doesn't happen straight away. What happens is the star, the main sequence star, runs out of hydrogen and becomes a red giant. Now, this is quite a simple version of what a red giant is. When the hydrogen runs out, fusion stops. When fusion stops, that means thermal pressure reduces greatly. So now gravity is much bigger than thermal pressure, and therefore in the core of the star collapses. As the star collapses, just like here, the temperature increases and the pressure increases, and it increases to a point where helium can now fuse. So He can fuse to heavier elements. In the outer layers of the star, thermal pressure is bigger than gravity. The outer layers tend to puff up, which makes it a red giant. And because it's red, that means it's cooler than when it's main sequence, because a red object is cooler than a yellow object in a yellow star. So the outer layers puff up, the inner layers contract and heat up, therefore allowing helium to start fusing. And helium will fuse to make elements like carbon, oxygen, nitrogen, not just helium. They'll have different combinations that fuse to make this. When helium runs out, it'll start to fuse lithium. When lithium runs out, it'll start to fuse the next one. I'm not a chemist, I can't remember which one that is. And so on. But eventually it'll get to a point where it can't fuse anymore. It can't contract and heat up anymore and fuse any more fuel, and it will run out of fuel. And when it runs out of fuel, I'm going to write helium and heavier elements. When it runs out of fuel, fusion stops. And technically the star is no longer a star. Stars are only stars when they are fusing, but we still continue to call them that. And when fusion stops, we're left with two things. We're left with this very, very hot, dense core. And that hot, dense core is known as a white dwarf. And then the outer edges that had puffed up, they are known as a planetary nebula. So I just knocked that. Move that back. The word nebula is there again. Nebula meaning a cloud of gas and dust. The planetary nebula will float away and go into a stellar nebula and potentially make a new star. And you're left behind with this white dwarf, which is very small, very hot, very dense. It's not fusing. A white dwarf is about the size of the Earth. So you've taken a star and squashed it down to about the size of the Earth. And over time, it'll eventually basically cool down. And as it cools down, it dims and dims and dims and becomes a brown dwarf. But you don't need to know about those. So this bit isn't going to do anything new. But the planetary nebula could go to a stellar nebula and then start the whole process again. Now, massive stars follow a very similar process. Everything's just a bit more dramatic and over the top. So massive stars, instead of having a 10 billion year main sequence, they still have a main sequence. Their main sequence is much shorter, maybe about 1 billion years. Depends on the size of the star. You'll also notice that the star here is blue. That's because a blue star is hotter than a yellow star. And the main sequence star, when it's a massive star, is hotter than if it's a medium-sized star because it's got more fuel, it burns through more of it. Once again, it's fusing hydrogen to helium. and eventually it will run out of hydrogen. And the same process happens. The core contracts because the pressure decreases because hydrogen stops fusing. There's no thermal pressure, or it reduces a lot, until it gets to a point where helium can start to fuse. And then it goes up to heavier elements. So you find in a red giant, and also this is called a super red giant or a red supergiant. Either way is okay. You get these kind of like shells of where the different fusions are happening. So in the centre you have the hardest fusions going on, the heaviest elements, and then you get shells of where the fusion is slightly easier for things like helium and lithium. Now a super red giant will keep on contracting, the inside of it will keep on contracting and fusing heavier elements up to when it gets to iron, which has got an atomic number of 56. The outer layers, just like over here, puff up and make the star super big. Hence the name super red giant. But inside it'll keep burning until it hits iron. So it's fused all the helium to make maybe lithium, the lithium's fused to make oxygen, the oxygen's fused to make hopefully nitrogen's one of the next ones, nitrogen's gone to carbon, whatever the order is, I think oxygen's after carbon. But eventually it'll get to a point where we're fusing to make iron. Now you can't fuse iron to make anything heavier. If you have done radioactivity yet, you'll know why. It's to do with the fusion-fission curve. So when it hits iron, there's a bit of a problem. When it hits iron, it can't contract anymore and get any hotter. Well, it can contract more, that's going to be the problem, but it can't fuse anything else when it gets hotter. So when it hits iron, fusion stops. And when fusion stops, thermal pressure decreases, gravity pulls the star in, and it pulls it in at such a rate that we get this here. This is a supernova, which is a Roman word or a Latin word for super, big, and a nova, new, big new star. And the super red giant, fusion stops, the inner cores, basically, or the inner core contracts, collapses, and the star collapses in on itself, and all the different layers bounce off each other. This is a very, very simplified version of what's happening. And we get this massive explosion, a supernova. And a supernova is the biggest and brightest event that we know of in the known universe, really, or common event, to be fair. Supernovas happen about once per century per galaxy, which shows that they're pretty rare because there's hundreds of thousands of stars in galaxies. And we can sometimes see them. If there's suddenly a bright new star in the sky that's there for 4 or 5 days, it's probably a supernova. We can't predict exactly when they're going to happen, but if we see a sudden star appear for a short period of time, because in space, in the age of the universe, 4 or 5 days is pretty fast. That's a supernova. There's rumours that in like the 1500s there was one which made the sky so bright that it didn't even go dark at night. So it was on the opposite side of the Earth to the sun. So in the day you had the sun, and then when you turned around to not face the sun, you now had a supernova. And so it didn't go dark for days. There's also ideas that maybe the star of Bethlehem was a supernova, a star that arrived for a limited period of time, was very, very bright. So anyway, the supernova is the dramatic cousin of the planetary nebula. But as the planetary nebula just floats away, the supernova ejects all that gas and dust into, surprise, surprise, some other nebula. So the outside, can then go on to produce more stars. Now, there are two things that can be left behind. So just like before, the planetary nebula leaves behind a white dwarf. If you've got a small massive star, so it's still bigger than the sun, but it's a smaller side, you will go to a neutron star. So that's what's left behind. Now, a neutron star is made of neutrons, hence the name. Whereas a white dwarf is like taking the sun and squashing it into a planet, a neutron star is like taking the sun and squashing it into an area the size of Manchester, so a large city. So it's very, very, very dense, very, very, very hot. Or if you have a really big star that's supernovas, you get to the famous black hole. And a black hole theoretically doesn't really have a volume. It's a singularity. It's so small that it's just a point. In reality, it probably isn't. And so you've got the mass of an entire star squashed into this tiny, 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 tiny space. So it must be super, super, super dense. And because it's super, super, super dense, it has an awful lot of gravity. And black holes have got so much gravity that it can suck in light from nearby, even though light doesn't have mass and therefore technically shouldn't be affected by gravity. But general relativity and things like that show that that's not the case. So neutron stars are for smaller massive stars and black holes are for bigger massive stars. And this whole process takes about the 10th of the time-ish than for a medium star. So that's stellar evolution. And back in the day, like, 100 years ago or so, astrophysicists and scientists didn't realise that stars did this. They just thought there were different types of stars. If you look at the sky, usually through a telescope, not just the sky at night, they noticed that some stars were bigger and some were smaller. Obviously, some were just further away, but they noticed that there were different colours of stars, different sizes, and they knew that different colours of stars were different temperatures. If you think about heating up an iron nail when it's cold or even when it's quite hot is just grey, it's iron. But as you heat it up more and more, it starts to emit visible light. It emits red light, and then orange light, and then yellow light, and then white light, then blue light if you got it hot enough. Think about a Bunsen burner flame. The hottest part's the blue part. So they knew that these different colours of stars were different colours because they're different temperatures. And they knew that there were different brightnesses and different luminosities, which we'll come on to. And they tried to classify stars in a certain system. Now, this system you don't need to know well at all. There's lots of different letters like L stars, M stars. I think originally they had them all in alphabetical order, A up to wherever, and then they realised the order was wrong. So the order isn't in alphabetical order, the order of the stars. It's quite a funny one. But what you do need to know about is that was a bit awkward. So what happened is somebody, or two people, called Mr. Hertzsprung and Mr. Russell, decided to plot these stars on a diagram. And this is where we start to get an idea of stellar evolution. So the diagram that they went for, or the graph that they went for, is a luminosity temperature graph. So I'm just going to write my axes on. I'll move this back in a second. So we've got luminosity. Now, luminosity, if you haven't covered that yet in your space course, is basically the power output of a star. It's measured in watts. So the more energy that the star gives out per second, the higher the luminosity. And it will give out more energy if it's brighter, but also if it's bigger, because if it's bigger, it's got more surface area to give that light out over. Here, I'm going to measure my luminosity in this L circle with a dot. This circle with a dot means solar or of the sun. So I'm going to measure it in terms of luminosity of the sun. And both of these scales are logarithmic scales. Because there's such wide ranges of temperatures and luminosities that I need to fit on a graph, I can't fit them on with normal scales, so I have to have a logarithmic scale. So in the middle here, I'm going to write 1. Now that means that any star along this line has the same luminosity of the sun, because it's 1 times L0. Then I'm just going to split this up into mainly even steps, and I'm going to go up in hundreds. So this is going to be 100, or 10 to the 2, and then this is going to be 100, which is 10,000. This is going to be 100th, which is 0.01. This is going to be 100 hundredths, 0.0001. I hope that's correct. If it's not, I apologise. And it can carry on. You can go up to 1 million here. And I've not really left enough room for 0.01, but there we are. So what we're saying here is that a star along this line would have 100 times the luminosity of the sun. A star along this line would be 10,000 times the luminosity of the sun. So much brighter. So up here, I'm going to change colours now to try and show some difference. Basically up here, you've got very bright stars. And down here, you've got very faint stars. I think that's how you spell faint. If it's not, I'm really sorry. Then they wanted to plot luminosity or brightness against temperature. Please look at the temperature axis. You will find that I seem to have done something wrong. So temperature, it's measured in Kelvin. If you put degrees here, it's really not the end of the world because the scale we're looking at, they're basically the same. But temperature, you'll notice, is going this way. We go, strangely, from hot on this side to cold on this side. And once again, the scales are logarithmic. They don't go up in even patterns. So I'm going to start in the middle, then do some evenly spaced gaps, like so. And you do in the exams need to know kind of what kind of scales you'd be using here and be able to sketch this graph. So we start in the middle here. I'm going to put 10,000 Kelvin. And then instead of here I went up in hundreds, here I'm going to double. So I'm going to double as I go up. So here I'm going to go 20,000. And then here I'm going to go 40,000. And going backwards, I'm going to halve, so 5,000 and 2,500. So each time I've gone, I've doubled, whereas here each time I've gone, I've 100s, which is what makes it a logarithmic graph. So we've got cold stars to hot stars. And what they did is they took all the stars, they looked at their luminosity and their temperature, and they plotted them on this graph. And they found that a pattern emerged. Now you need to be able to sketch this graph. I would very much recommend looking in a textbook for what it really looks like, because I can't draw all the plots. But if you sketch it, it looks something like this. There's a line. You can draw it as a straight line, but it's slightly curved that goes through the centre diagonal. Then there are two little sections up here, like so. And then there's a section down here, like so. Now you need to know what each of these sections stands for. This line here is the main sequence. And they found that about 90% of stars fitted on this main sequence. And that's what started to give them the idea that maybe stars actually change over their lifetime, and that if 90% of stars are on the main sequence, that suggests that they spend 90% of their time as a main sequence star. Now I said before that our sun is slightly smaller than average star, which is true. The luminosity of our sun is 1 times the luminosity of the sun, and this is about where it fits here. So it's a terrible, terrible cross. So the sun. And it should be between 10,000 and 5,000. The sun's about 7,000 Kelvin, so that's in about the right place. So the centre-ish of your diagram should be the sun, a little bit over on your 10,000 on your Kelvin scale, because it's a slightly smaller than average main sequence. Average would be here. Massive main sequence stars would be up here, so blue ones would be more this way, and then sunlight ones are down this way, because blue ones are hotter because they're blue, and brighter. Now that brings me on to, if I walk along the bottom here, I can actually add in some colours for the different temperatures. 2,500, we're looking at kind of red, that's the colour of the star, and then 5,000, 10,000, we're looking at yellow, which is why the sun is a yellow star. Then we're starting to hit white about here, and then blue about here, which is why the massive stars are up this end, because they're blue. Now that can help us work out what these must be. Okay, this section here, we have got some stars that are bluey white, and that they're quite faint compared to the sun. So this section here is actually the white dwarfs. I spelled that, I've just written white dwarf, and if I put an S, it's wrong grammatically, but you understand what I mean. So this is the white dwarfs, and they find about 10% of stars fit here. This suggests that most stars are normal size main sequence stars, that massive main sequence stars are rarer, and that stars spend about 10% of their lifetime on that point. So you've got a hot star that's quite faint. Over here, these stars are red, and what we find, therefore, hopefully it's understandable, guessable which ones these are. We have red giants and red supergiants. Now, this globule is hotter than that globule because it's higher up on the luminosity scale, which means these are the red supergiants, ironically written in green, and these are the red giants. So we have quite cold stars, but they're very, very big, which means they're very luminous because they've got enough space that they can give off their brightness from. So this is the Hertzsprung-Russell diagram, and you need to understand the main features of it. You need to know about the scales, you need to be able to sketch it and be able to say that where the supergiants are, where the white dwarfs are, and if they gave you a star, so say for example they said, here's a star, what type of star is it? You'd have to be able to say, well, that's there, so it's a main sequence star. And if it was here, you'd have to say it's a white dwarf. And if it was here, you'd say it's a red supergiant. Another thing to think about is how stars travel around this diagram during their life cycle. They don't just stay still. So when a star is born, it is born in a cloud of gas and dust that is pretty cold, and it's also very faint. So when it's a protostar, it's down here. When fusion begins, its temperature increases and it becomes brighter, so it moves to the main sequence. Now, a normal sun-like star would move to where the sun is, so along this point. Then, when it gets to become a red giant, it moves up here, and then as a white dwarf, it moves down here. So it follows this kind of path. A more massive star will also start down here as a protostar, but it will journey its way up to the top of the main sequence, then towards a red supergiant. Then there's a supernova. Think about what a supernova is. It's the biggest explosion you can pretty much get in the universe. It's very, very, very bright. It's very, very, very hot. It's so hot, and I should say this, is that every single element that is not iron, or less than iron, that's heavier than iron, the only place it can be made, as far as I know from my knowledge of space, is a supernova. There's some talk about them being made in neutron stars, which I haven't read up on that enough, but the supernovas are so hot that they can force iron to fuse to make, to join to make other elements such as uranium, gold, silver, anything like that has to be made in a supernova. So you've got a super, super bright, super, super hot explosion, so we need to have the highest temperature, the highest brightness. A supernova would be up here. And then let's think about a black hole. A black hole is super dense, which means it's really, really hot. So it's on this side still, but we can't see it. It's black, which means it's really faint, so it moves down here. So the massive star has a much more dramatic turn around the graph and also takes a lot less time. So that's mainly it. A lot of this is from GCSE, but with just more knowledge. So like I say, remember, make sure that you know this stellar evolution sequence and you can describe it for 6-mark questions. A little bit of detail is useful about collapsing cores, etc. But you don't need to be able to talk about it in masses of detail anymore. The new A-levels, or at least mine, has reduced that knowledge a little bit. But you do need to then know how you put those stars onto a Hertzsprung-Russell diagram and make sure that you can draw your own with these axes and with this kind of pattern. And I would encourage you to have a look at a proper one so you can see how it's different to a sketch. Hopefully that was useful.